Hi everyone, good to see all of you again. Today's topic, what we're going to learn is this thing called quadratic inequalities. Well, in particular, how do we solve a quadratic inequality? But before we begin in that, let us first recap on something that we're all familiar with, like quadratic equations. Okay, now let us consider a function fx equals to x minus 1, x plus 3. Now, if I were to ask you to solve, right, solve fx equals to 0, then we have, well, x minus 1, x plus 3 equals to 0. Well, it's pretty easy for us to solve because from there we can tell that either x minus 1 equals to 0 or x plus 3 equals to 0. Therefore, we have x equals to 1 or x equals to negative 3. That sounds pretty simple. Now, translating this idea into a graph, then we will have a quadratic graph that looks like this, whereby the x-intercepts are x equals to 1 and x equals to negative 3. This is the quadratic curve. Now let us extend this question. How do we find the values of x such that fx is greater than 0? How do we find these values of x? Right now, if we were to approach this in a substitute a random value of x method, then we will be having this table here. Alright, now we already know that when we substitute x equals to 1, x equals to negative 3, fx would be equal to 0 for, well, obvious reasons. Now, if we were to sum in any other values of x, so let's say you want to sum in a value greater than 1. Let's pick a number, or any random number. Let's say, for ease of purpose today, let's pick 2. So if we substitute in values of x equals to 2, alright, now fx will be 2 minus 1, which is 1, 2 plus 3, which is 5, 1 and 5. So fx will equal to 5. Now this will be a value greater than x. No, this will give me a value greater than 0. Okay, cool. Now how about any values in between here? In between negative 3 and 1. Let's pick another number, let's say 0. Okay, now what happens when x equals to 0? We have 0 minus 1, which is negative 1, 0 plus 3, which is 3. So negative 1 times 3 will give us a negative 3. Now this gives us a value less than 0. Not exactly what we're looking for, because we're looking for fx greater than 0. Let's try that number. Maybe if we go further negative a bit, maybe negative 1. What will we get? Okay, negative 1 times negative 1 get negative 2. Negative 1 plus 3 get 2. So we will have, negative 2 times positive 2 gives us negative 4. Once again, it doesn't give us a positive fx value. So most people will think, hey, if I want to go more negative, then I won't get any negative values. Well, hold your horses on that. Maybe let's try something which is more negative than negative 3. Let's say, for example, let's take step by step. Negative 4. Now, if I want to sub in negative 4, then I'll have negative 4 times negative 1. Negative 5 doesn't look very promising, well, because it's really a negative number. However, if we want to sub x equals negative 4 here, we have negative 4 plus 3, now it's negative 1. Negative 5 times negative 1, when x equals to negative 4, we end up having a positive number. We get positive 5. Hey, are we getting somewhere here? We realize that, hey, if I were to have sub in any value which is greater than 1, we should be getting a positive value. We sub in any x value which is less than negative 3, hey, we also get a positive value. If you're not so convinced, let's try a much larger number, negative 10. Okay, now sub in negative 10 to here, we have negative 11 times negative 7. Hey, negative times negative is positive. So we end up having a positive number. What is it again? Negative 11, negative 7, positive 77. So it seems to hold that if I was sub in any x value less than negative 3, we will get a positive fx value. We sub in any value more than 1, we get a positive value. Now, is there a faster way as opposed to, hey, substitute? To what end do we substitute? Here is where we need to translate this idea of substitution into a graph. We'll do a quick sketch of the graph to help us understand a lot better. So earlier on, we've seen a quick sketch of the quadratic graph of fx. It gives us, well, something like this, whereby the x-intercepts are 1 and negative 3. Now, if we were to sub in any larger x value, or a value of x larger than 1, the graph will be on the positive side of the x-axis. Anything above here is positive, anything below here is negative. Alright, so if we were to sub in any other x value greater than 1, hey, we actually get a positive fx value. And conversely, if we were to sub in any value less than -3, we also get a positive fx value. When does it happen when we get a negative fx value? It's when we substitute a value that is between -3 and 1. This area here is a negative value. So answering the question from just now, what are the range of values of x such that fx will be greater than 0? The answer would be x greater than 1 or x less than -3. So from here we will see that the main solving technique that we're having here is to do a quick sketch of the quadratic graph and then identify which are the positive and negative regions. Suffice to say, we will need to use our knowledge of factorization factorization of a quadratic expression to be able to solve such questions so that we are able to do a sketch of the graph. Right, our first example in this video that we're going to take a look at is this. Right, find the range of values of k such that x squared minus kx plus k plus 3 equals to 0 has real and distinct roots. Now, we will need to bring in something that you would have learned before, which is called the discriminant. In a general form of a quadratic equation, ax squared plus bx plus c, the discriminant is b squared minus 4ac. We will need to use that to be able to solve this question. Alright, we need to find the range of values of k such that this equation has real and distinct roots. So the first thing we'll need to identify is what is the discriminant. But before we can do the discriminant, we need to identify what is its a's, b's and c's. So in this case, we will realize that the coefficient of x squared is 1, so therefore a equals 1. Right, the coefficient of x is negative k, so b equals to negative k, and the constant term is all those which are free of any x terms, which will be k plus 3, so therefore c, our c is k plus 3. Alright, so right now we can determine what is the discriminant. So the discriminant, b squared minus 4ac equals to negative k squared minus 1 k plus 3. So let's just simplify this. We'll have k squared minus 4k minus 12. Alright, now going back to the question, we are asked to find the range of values of k such that this has real and distinct roots. Now, for a quadratic equation to have real and distinct roots, it means that the discriminant has to be greater than 0. So, for real and distinct roots, b squared minus 4ac equals to 0 is greater than 0, which means our k squared minus 4k minus 12 has to be greater than 0. From here, what do we have? We have a quadratic inequality. We need to use something that we just learned earlier in the video to solve this. But we have a problem. This is a general form. What we see earlier on was a factorized form. Well, that shouldn't be difficult for us, right? So we just need to factorize this quadratic expression. Factorizing this, we will have k minus 6 and k plus 2. Okay, we now have k minus 6, where k plus 2 is greater than 0. Now from here, it's still a little hard for us to be able to tell without sketching the quadratic graph. So let us first sketch out the quadratic graph to help us identify which are the range of values of k that we're interested in. Okay, so if you were to have a quick sketch, this is a positive k graph, k square graph. So we will have this, and the the k-intercept in this case would be 6 and negative 2. Now we are interested in the range whereby this expression or this part of the graph is greater than 0. So we are interested in this area and this area. Okay, so what are these range of values of k? Here will be k greater than 6, and here will be k less than negative 2. So now that we've gotten this, With many thanks to our quick sketch of the quadratic graph, we therefore have the answer k less than -2 or k greater than 6. There we have it. The next example, find the smallest value of the integer p for which px squared plus 7x plus 3 is always positive for all real values of x. This question is actually slightly a little trickier. You need to understand a few things about what does it mean by a quadratic expression is always positive for all real values of x. A quadratic expression, we can always easily translate it into a graph. So now notice that in this question, it says it's always positive. So in your head, you know that a quadratic graph can look either like this or like this, whereby this part extends out, this part always extends out, right? So for a graph to be always positive, in your head it could either look like this, whereby this x-axis is below the graph, which means this guy is always a positive, or it may look like this, but here's a catch. This can't ever happen because these two ends will still continue to extend further and further down. So hey, this is negative, so this can't be possible at all. Okay, so we're actually looking at this type of graphs. Alright, now conversely, if we have a graph that's always negative, then this is an always negative graph. So to minimize the confusion for all of you, this is always positive and this is always negative. Now, in either of, regardless of the case, what do you realize about the roots? You realize that there are no real roots because the graph does not cut the x-axis in either of the cases. Now, that is the key ingredient to solving this question. So in short, we have the quadratic expression. We want this to be always positive. So we realize that this fella would need to have no real roots. No real roots means that the discriminant will be less than 0. So it's p squared minus 4ac has to be less than 0. So what is b squared minus, what is b squared minus 4ac? b will be 7, so it will be 7 squared minus 4 times p times c, 3. Right? Less than 0. Alright? Solving which, what will we have? Well, just do some quick arithmetic here. 49 minus 12p less than 0. Let's change this to a mixed number so it's a lot easier to see. So we have p greater than 4 and 1, 12. That isn't the end because the question is asking for the smallest possible integer value of p. So if p has to be greater than this, that means the smallest possible integer value of p will be 5. So therefore, the smallest integer p will be equal to 5. Now, let's do a quick recap on what we have. What's the main ingredient in solving such questions? Now, earlier the question says that you want this expression to be always positive. Always positive in a graphical sense would mean that the graph has to be always above the x-axis. The graph can't be touching the x-axis at all because once it touches the x-axis, then it will equal to 0. 0 isn't positive, neither is it negative. So we want it always positive. Conversely, if you wanted a negative, always negative question, then this graph will be here instead. In either case, it will not be touching the x-axis. It will not have any real roots. Therefore, when we say it's always positive or always negative, the next thing we need to think of next is that we have the discriminant less than 0 because there's no real roots. From there, we solve, we get the answer. This is the main key ingredient. Alright, our last example in this video will be this. Find the largest value of the integer k such that kx squared plus 9x plus k is always negative for all real values of x. So as we've covered earlier on, that when we wanted something always positive or always negative, we should be drawing the graph, sketch it out. We want something that's always negative. The graph will look like this. Then we will notice, hey, sad face graph, negative. So this will imply something about the coefficient of x squared. It has to be negative. Coefficient of x squared is negative. Bear this in mind, going back to the equation, which is kx squared plus 9x plus k. Okay, we want this to be always negative. It means that this fellow has no real roots. No real roots means that this discriminant has to be less than 0. From here onwards, substitute, solve, and we'll see what we get. Okay, B is
9, so we have 9 squared minus 4k. Well, how boring. Okay, solving simplifying ways, we have 81 minus 4k squared less than
0. We can factorize this. Hold it, let's make life easier. Always try to put this in front and make it positive so it's easier for us to handle later. So we will have 0. Now why is this happening? Because we are multiplying by -1 across the whole inequality. So when we multiply by -1 across the inequality, or any negative number across the inequality, the sign of the inequality flips from less than to a greater than. A very small thing that most students tend to make a mistake on, so please bear it in mind. From here, we can factorize this because it's the a squared minus b squared type of expression. So we would have to same old thing that we always have. We can do a quick sketch of this graph. Now, a quick sketch of this graph would be like this. 2k plus 9, which means that it's either 4.5 or negative 4.5. Okay, we want this to be greater than 0. Oh wait, let's just put the k here, let's just put the x here. Alright, maybe at this juncture you'll be wondering, hey, why do I have a graph which is different from this? Now take note, this graph is with respect to x, so this graph is with respect to x, but this graph is with respect to k, so they are two entirely different graphs altogether. So at this point we are interested in the k, a quadratic expression with respect to k, not the x one. Okay, so from here we will realize that we want this to be greater than 0. We are interested in this part or this part. So therefore we are interested in this portion or this portion, which means k has to be greater than 4.5 or k has to be less than negative 4.5. So let's take a look at whether we have answered the question here. Now we want this such that it is negative for all values of x. Now you will notice that here I've written the coefficient of x squared is negative. What happens if it is positive is we end up having a smiling face graph, not a sad face graph. So looking at this answer that we have, and here we realize that this k has to be negative, not positive, which means we can't be having this answer, we would have to reject it. Then that leaves us with this answer whereby this k has to be a set of negative values, which means from here we would have to. So therefore, k is less than negative 4.5. So to find the largest value of the integer k has to be negative 5. So negative 5, not negative 4. Negative 4 is larger than this, so it doesn't satisfy this inequality. So the largest possible integer k would be negative 5. And this would answer the question. And just a quick recap of what has happened. Alright, now find the largest value integer k for this expression such that it is always negative. Now that key word always negative. This expression always negative would mean that a quadratic graph has to be first a sad face and always below the x-axis. That's why we do a quick sketch here to remind ourselves that it has to be a negative x squared coefficient. Okay, it has to be like this. It has to be a sad face graph with a graph not cutting the x-axis. It means no real roots. No real roots means that the discriminant has to be less than 0. So this is the main key step. No, this is the main key step number 1 to infer from the question using the expression. And then the key step number 2 is linking the concept of discriminant so that we can use b² minus 4ac less than 0. From here onwards is a standard procedure of solving. Then comes the next new part that we are learning, whereby we are solving quadratic inequalities, and then we just solve it as how we're supposed to solve it. Then comes to the last part, which is the slightly trickier part that most students would tend to forget, to reject one side or value of k because we want the coefficient of x squared to be negative. After which this done, then the last part k equals -5, then yeah, that's about it. Yes, so this ends the video on this ends the lesson on quadratic inequalities. If you have any further questions, please do drop some comments in the comments below. Yeah, and I'll see you next time.